יום השואה ב10 באולם וייס. ב10? ב10. עכשיו, אם מישהו, כן, אם אתם רוצים, כמה מכם רוצים להשתתף בזה, אז אני אפסיק 20 ל10 ונחדש ב10:30. אם לא, אז אני שואל. אז פשוט אני אדע שב10 נהיה בחוץ לצפירה. אז יש מישהו שרוצה ללכת לטקס? כי אם כן, אז אני אענה לזה ונעשה הפסקה של 3/4 שעה. מה? מספיק אחד שניים שרוצים, אז אני... מה שתגידו. כן. כן? כן. אתם הולכים על זה. זה לא...
חבל להציג גבעת?
מה?
חבל להציג גבעת?
לא. בסדר. אז אנחנו עכשיו נתחיל, נעשה הפסקה, וב10:30 נמשיך. עד 12. Okay. So now we are, it's been a long time. And I hope you had a good vacation, a good holiday. And the last time what we did was we talked, I'm not going to repeat each time, that we are talking still about networks of binary neurons, that we already established a certain notation, that they are connected with these binary neurons. We adopted this physical metaphor of magnetic spins, and therefore the state of each binary neuron could be either plus or minus 1, that the interaction between these binary neurons is determined by these parameters JIJs, which are the synaptic efficacies. And what we are now doing, we are exploring the dynamics of such networks, and the basic element MI that we defined is the average. Now, we shall use this notation for average in different meanings, and therefore it is important to specify what we mean. An average could be kind of an arithmetic average over the whole system, but what I mean here is the thermodynamic average. And the thermodynamic average is defined, what I mean by this SI, just to remind you, is the sum over all possible configurations, so to the n of them, of the value of SI in that particular configuration times the probability of having that configuration, and T denotes the time. And so this is MI. And this depends on time, and of course in equilibrium we know already that in equilibrium the PI in equilibrium as time goes, asymptotic in time in equilibrium, this will be the P equilibrium, which is the of I, which is the Gibbs distribution 1/z e to the minus beta e of I, and G is sum over I. So this we already, yes. כן. אפשר, אתם יכולים עברית, אני אדבר אנגלית. Yes. I guess I'm still doing it in English, although that I don't know if there's anybody here, but this is recorded, and there are students who depend on this. Okay.
So in the first equation, when you sum over I,
yes,
and when you go only SI, you go only on the
site I. I now is a specific, I mean, lowercase I. This is a specific bit. I look at this site, and I want to know what happens at this particular site as time goes on. Yeah. And then, of course, and then we found, and that's the result that we derived last time, that mi is a function of time, and by this I denote the time derivative is equal to minus mi of t plus the hyperbolic tangent beta h beta, say, hi, yeah, where this is the same kind of average. This is the thermodynamic average. And hi is defined as sum over j, jij, sj plus hi 0, which is a kind of an external input, external field, acting on site I. And then we said the following. We adopted the so-called mean field approximation, and that is that we replace the average of a function of x by the function of the average of x. And I said a few words about that. In physical system, this is an approximation. In some cases, it's a very poor approximation. Nevertheless, it's a cornerstone, a beginning of investigation of the behavior of magnetic systems. In our case, this is not even an approximation. And it is not an approximation in a physical system where everything interacts with everything. In physics, we call these long-range interactions. Usually in physical systems, when you have a crystal of magnetic spins, one spin interacts with its neighbors, maybe next nearest neighbors, maybe next nearest neighbors, but then the interaction dies off with distance very fast. And in that case, this is not a good approximation. The longer the interaction, the better this approximation is. And in our case, since we assume that everything interacts with everything, one can show that this is even exact. And therefore what we have here, and this is our final... That's what we said. We at the beginning, not at the beginning, when we started that, we talked about different architectures. And we had a kind of layered architecture, but then we had an architecture with a lot of fields. And in those architectures, at least first we assume that every neuron will interact with all the other neurons. In the course of this course, as we proceed, we shall relax many of the basic assumptions. So this is not a very accurate description of what actually happens. I mean, there may be 10 to the 11th neurons in the cortex, but every one interacts with 10 to the 4th. So it's a very sparse connectivity in that sense. So we should look at models of that kind later. But at this stage today, everything interacts with everything to make things simple. So what we have here, and this is where we are now, is M I T, M I of t equals minus M I of t plus the hyperbolic tangent of beta j. I now use the explicit form of hi from here. And again, to make things simpler, at this stage, I shall ignore hi 0. So I take this now here, Jij, and remember, this is the Fj, but now I took the thermodynamic average, inserted it into the hyperbolic tangent, so the thermodynamic average is over this, and the thermodynamic average of the Sj is Mj. Now you see we have, and everything now depends on time here, this also depends on time. So you have n coupled differential equations that describe the dynamics. In equilibrium, nothing changes with time anymore. So in equilibrium, we expect to find Mi, and now I drop the time dependence because we are in equilibrium. Equilibrium, this is 0. Mi equals the hyperbolic tangent of beta Ji, beta Jij Mj. And now, to proceed, we would like to say something specific about the Dijs. And this takes us to the Hopfield model. And in the Hopfield model, we assume that the Dijs, we assign to the Dijs, oh, let me say before that. Before I do that, let me tell you that now, if our goal is to use or to apply this system, this network, to imitate a memory. We would like to use this as a model for a memory. And we assume the following. You see, there are 2 to the n configurations. And we assume that among those 2 to the n configurations, there are p configurations, which I denote by mu from 1 to p, from 1 to p. They are specific configurations. I should tell you immediately how I select them. And these configurations, in this configuration, I denote the bits in these configurations by psi. You see, whenever you find the notation S, it is a variable. S is a dynamic variable. S changes. A configuration S1, S2, S3, and so on is one particular configuration, and the dynamics takes us through the landscape or through the space of all such configurations. Now I assign to certain configurations this specific psi I mu, psi, and this will be again, xi 1, xi n, mu, and there are p such specific configurations. And the idea is the following, that if we schematically depict the space of all configurations here, n is the number of sites. Here, n is the number of sites, the number of neurons. P is the number of configurations that I choose. The idea is that every such configuration is a representation of some cognitive concept or something stored in the memory. And these configurations are certain points in the space. Every point here is one configuration, and certain specific points are the ones selected. And the idea is the following. There is a certain stimulus to which this system is exposed. And that stimulus imprints on the system an initial configuration, which I denote now. Which I shall denote by S I, at time 0. Si at time 0. This is a configuration. Suppose this is this one. So at time 0 the system is in this configuration. Now the dynamics begins. And this goes to Si t as time goes on, and ultimately what we would like to do is that ultimately it will go to one of these concepts. I mean, naturally to this one, because it's very close to here. If we start from here, it may go to this concept. So the whole idea here is that our space of configurations is divided into certain domains of attraction. These would be the attractors of the dynamics. If my stimulus brings me into one of these domains of attraction, then I would like, the dynamics to take me to one of the selected configurations which represent a concept, and then I say I retrieved something, I recognized something, I did something which is cognitively meaningful. So this dynamics is a certain example of we calculate these attractors. And in order that a system will behave like that we will have in the system many such attractors, and this is what we would like to have, because we want a memory with a large capacity. The system has to be very non-ergodic. And I don't know who was here at this, at the exercise Targil on Tuesday, and I think on Tuesday we explored with you this concept of ergodicity, but let me just tell you what ergodicity means. Ergodicity, an ergodic system is a system in which the asymptotic behavior does not depend on the initial condition. Physical systems in general are ergodic, in general. What we need here is a very strong behavior on initial conditions. System in which the asymptotic behavior depends strongly on initial condition is non-ergodic. We need a kind of breaking of ergodicity. In physics, breaking of ergodicity is connected to phase transitions, but that's all that's necessary for you to get from this method. That we are looking for a system, and we want to verify that our system indeed is highly non-ergodic, namely that we can embed in this system many such attractor configurations, and that the dynamics, the asymptotic dynamics of the system strongly behaves on the initial conditions, which was established. In a paramagnetic system in physics, no matter where you start with, you will explore the entire space. So this is what we have these concepts. And now, 6 minutes. And now I want to do the following. So we know this. So now I am assigning to Jij a specific value. 1 over n mu psi I mu psi j mu. So you see, we should use this particular value of Jij. Now, I mentioned several times in the introductions and later that essentially the Jij's are the result of the learning process. And the learning process proceeds via the Hebb's principle. And Hebb's principle tells us something about Jij depending on the activity of the presynaptic neuron and the activity of the postsynaptic. Namely, the Hebb's principle tells us that if one neuron is active and the second neuron which is connected to it as a result of that is also active, and that happens over time, then the synaptic efficiency, the Jij, will be Jij plus a certain, let me say, should be S1 plus 1, S2 plus 1. So you see, this is the activity of neuron 1, the activity of neuron 2. You can divide it by 4 if you so wish. This is a certain parameter, delta. So each time that S1 and S2 are both active and they are connected, Then, see, when they are both active, this is 1. When one or neither of them is inactive, this is 0. This is called a potentiation of the synaptic efficiency, an increase of the synaptic efficiency due to learning. There are also other versions and other now extensions of this. What we are doing here is imitating the Hebb principle in the sense that Jij is determined by the pre- and postsynaptic activity, but in a way which is artificial, and at least in one case is nonsensical, because this tells you that if both are inactive, -1 and -1, nevertheless, Jij increases. Yeah. So this is not a biologically plausible assignment for a Jij. It is, we still adopt it. It's very convenient, and with this kind of assignment, we can develop a very, very rich phenomenology, and later, as I told you, we shall relax a number of such conditions to make our models more plausible biologically. At this stage, all we are interested in is to adopt the minimum that is essential, the activity, the inhibition, the excitation, the neurons, the connectivity, and see what kind of phenomenology we can derive. And this is a very useful kind of assignment. You see here, Jij is not given as a process of learning. It is engineered, it is put into the hardware, and now we would like with this to, to assume the dynamics, and let me write the last equation, and I will let you, and we'll have so now we have this Mi is equal to hyperbolic tangent beta psi I sum over mu psi I mu sum over J psi I psi J mu mj. So this is the equation. Yes? Yes.
Shouldn't be sum over I?
No, there's no sum over I. I is here. I is for every site we have such an equation.
Oh,
Okay. So as I said, I'm taking a break now. Everybody who wants to go to the ceremony, Ulam Weiss, should do it now. We meet again at 10:30 here, and then continue to 12. Okay? כן. בינתיים כן, מי אמר לך? אני לא אמרתי. כי יהיה יותר גדול. כי יש לנו 2 בחזקת. לא אמרתי. לא, לא שהמערכת יכולה להיות, שאני בוחר. מתוך אלה שיכולה להיות.
ואז אנחנו מייצגים כל וקטור נוסף כזה,
כן.
החוזק בין הקשרים הוא בעצם נקבע רק לפי מה שאתה תגדיר לי כמצבים של המערכת הישראלית.
החוזק?
החוזק של
כן, 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 כן. כי אותם למדת. רק אותם למדת. אלה הדברים שהיית צריך ללמוד.
אחרי שלמדתי.
לאחר שלמדת, רק אותם למדת. בדיוק לחלקים.
שזה פשוט מכפלה בין הבקטורים?
לא, לא מכפלה.
סכום של
יו. זה לא מכפלה שלה. ארגוני.
העיקרון שלפיו אנחנו מעדכנים את המשקולות
הב, לא מעט הב. הרי היה לנו... כן, זה בשיעור הראשון, סיפרתי לכם על... אני לא יודע מה, נתתי הרצאה על ההיסטוריה.
כן, כן, הייתי.
כל הסרט היה על אישה
אוקיי.
Organization of Behavior 1949.
תודה.
רציתי לשאול על הסטיים. אתה אומר שנתחיל באיזושהי סיטואציה מסוימת, ואז במהלך הזמן המערכת תתכנס לי לאחד המסוימים של הקסיים האלה.
זה מה שהייתי רוצה.
אז כאילו, האנרגיה של הקסיים הזה היא נמוכה יותר? כאילו, למה אתה יכול להניח את זה?
מה?
למה זה נכון? למה אתה יכול להניח את זה? כי אתה יודע שהיא...
אני לא יכול להניח שום דבר. מעכשיו כל מה שאני אומר אני אוכיח. אני לא הנחתי שום דבר. אני בניתי את זה, אני אראה לכם שזאת אנרגיה נמוכה.
כשאתה אומר זיכרון, אז זה כאילו זה סיטואציה של המערכת שואפת להגיע אליה?
כן.
כאילו זה זיכרון.
ואז שלפתי את זה מהזיכרון. אם המערכת בסוף, באופן הסימפטוטי, תתייצב,
על המצבים האלה, אז זה זיכרון.
אז זה הזיכרון.
אוקיי, אז זה הגיוני שזה אנרגיה נמוכה יותר.
או יש אנרגיה ובעד.
משהו שיעלה מהמשקעות?
לא,
כמובן זה וקטור של 10 בחזקת 12 אחדים והחוסים שאומר נוירון אחד פעיל, נוירון 2 סגור.
אני אגיד לך...
כי עכשיו הוא אמר משהו אחר, ואני לא מצליח...
זהו, עד עכשיו אין בכלל מצב, שעשינו אנלוגיה ל... כאילו, אני לא...
מה איתה? היא מבינה?
נהייתי כאילו...
בסדר, אחרי הספירה, חבר'ה, אחרי הספירה. על S.
אוקיי. אז S זה הספין.
בבודד?
בודד. שזה יכול להיות פלוס אחד ומינוס אחד. חשוב שלהם מה זה ספין ופלוס אחד ומינוס אחד. זה יום כאלה. אז
מה זה המצב של מערכת?
מצב של מערכת זה I, שזה כאילו איזושהי קבוצה סדורה, כן?
זה ה-I הזה?
לא, I גדול. I גדול הזה. מתחת לסיגמה. בתוך ה-I.
אוקיי. זאת אומרת, זה נגיד כל ה-100 מיליארד נוירונים שיש לי? מי עובד, מי לא עובד?
כן.
כן?
מ-1 ממינוס 1.
מ-1 מינוס 1 וקטור כזה נורא ארוך.
כן.
ומה זה J?
רגע.
סליחה, ה-J-I-J הזה, זה מה שזה אומר, נכון?
זה הקשרים ביניהם. תכל'ס זה הקשרים.
מה ההבדל בין I ל-J?
I לספין J, כן, בין SI ל-SJ, מה הקשר הסינפטי? כאילו זה באוריינטציה.
והם יוצרים את ה-I הגדול.
בודד. כלומר, יש לי כאן שני וקטורים.
כן, S ספין
איך
בודד,
נראית המודד
I
בעצם?
ספין בודד.
נכון, זה מטריצה.
J-I-J זה מטריצה.
פה אתה כאילו, לא רואים אותך.
שכאילו האלכסון יגידו אפס.
כבר מפעלים נטע ותמר?
אני עובדת, אני לא יודעת
מה?
מה.
אני לא מבינים אותו היסטוריה, אבל לא חשוב.
לא, כאילו
או אפס, או לא משנה.
כולם נותן אינקוט.
תקשיבי, אפשר עכשיו.
אוקיי.
קיצור, אבל זה כאילו משמעות של J. עכשיו, הקשרים האלה הם כמו שנדבר בלמידה, שכאילו זהו,
עוד לא מה שעשיתי. בסדר, ואז אם אנחנו עוברים לפה, אנחנו אומרים מה ההסתברות שבזמן T מקונפיגורציה מסוימת תעבור לתחום?
לא, בלי לעבור.
לא.
לא, הם לא הודיעו על זה
כי אני זוכר שהיה משהו PIT ל-PJT.
לא, זה היה...
זה הסתברות כאילו...
PIJ, PJI.
PIJ. זה כמעבר
זה
מ-J.
כאילו, זה לא משהו פה. כן,
הבנת
זה
למה זה...
הסתברות של I לעבור... כן, לעבור מקונפיגורציה.
אוקיי.
כן.
מה זה?
שכל מעבר כזה, חשוב זה
לא, אני מבין מה זה, אבל...
אתה רוצה שלושה מעברים. זה הסתברות כאילו... משהו כזה.
מה, יורד מנחת?
אז מה?
עכשיו זה SI. זה הממוצע.
זה כמו, אתה רואה כאילו כמו המיסוי של...
רגע, מה זה עוד פעם? מה זה SI?
ממוצע מה? לאורך כל המצבים האפשריים?
לא, אז ממוצע על מה? זה מה שאומר. אז זה ממוצע על כל הקונפיגורציה.
כל המצבים האפשריים. כאילו כל
כל הקומבינציות של ה-SI. זה כאילו ההסתברות של הקונפיגורציה. בערך של SI. ממוצע על I, כאילו על, אתה יודע, אינדקס 3, נגיד בקונפיגורציה, ו-S זה 3, בכל הקונפיגורציה.
יכול להיות שנורון מספר 3 תמיד עובד עם כולם, ונורון 2 הוא סולידי כזה עובד במקרים מאוד בודדים, אז הם אוקיי, בסדר.
רגע, מה הקשר לנוירון נודד? אין קשר לנוירון. SI זה המצב של נוירון מסוים.
המצב של נוירון 3 בקונפיגורציה 14. המצב של נוירון 3 בקונפיגורציה 15.
זהו, בדיוק.
זה ההסתברות שלך תהיה קונפיגורציה
אבל
זה שתיים
אפשרויות? זה עיגול כזה, ואז הוא אמר...
רגע, זה כל הנוירונים ששייכים
קונפיגורציה.
מה זה? זה אני מחליף את זה, זה פשוט? זה שווה.
כן.
אוקיי, זה מה?
לא, אני לא...
זה משפט שלנו.
לא, אנחנו...
אז מה המשמעות של נגזרת?
זה אומר שמתחיל מקונפיגורציה,
כאילו זה משהו
כלשהי,
ממוצע, גם ממוצע יכול לשנות זמן.
זה נגזרת על זה.
יש לך את הספינים.
לאחד ממה?
איזה הפחות זמן שנסתברו.
אני לא יודעת למה זה מתמטית, אני יודעת שבגלל שאומר, אני מחלקת כל מרחב.
אז הממוצע משתנה.
הרי
הרי אם עשינו מעבר בקטרת שלו,
אני לא יודעת אם זה...
אז כמה אני מבינה, אז ברציפית. הוא טוען שכיוון שהמערכת תלויה בהתחלה שלה, אז הדינמיקה שלה תהיה כזאת
זה תלוי ב-T. אבל זה קיים, זה ממש קיים מתמטית, אבל מאשר נראה לי כלומר, אני נשאר להדפיס אותו, או כאילו יהודים הושיעו נקמה, בדיוק. אוקיי, בסדר, אבל בסדר.
ראינו כבר
מה זה? מה זה? זה ההסתברות שלו,
זה ההסתברות להיות מצב I בזמן T.
מה זה אומר שהוא עובר למה? לאקוויליבריום? למה שבכלל משהו יגיע לאקוויליבריום? בסדר, יגיע לאקוויליבריום, מה זה זה?
זאת אומרת, היה אפשר לחשוב על ממוצע עבור זמן. זה שייך לפיתוח
זה, ולמה הוא גם מופיע פה, אם זה נראה בערך כמו זה, מה המשמעות של 1 חלקי
אוקיי, אנחנו דיברנו, לפחות
עכשיו עוד שאלה.
טוב,
למה זה מתכנס רק למצבי מינוס?
לא דיברנו על זה.
לא דיברנו על זה. אוקיי.
משהו כאילו נשמע מוכר, כן.
אוקיי, בואו
בואו
נניח המשל הפיזיקלי שלו. בואו נסתכל על נוירונים כאילו הם חלקיקים במרחב שמשפיעים אחד על השני, שהם יכולים להתנדדים כיוון השעון נגד כיוון השעון, ואז כל חלקיק יש לו השפעה מסוימת על חלקיקים אחרים. זאת אומרת, כשהוא מסתובב בכיוון השעון גם הם מסתובבים בכיוון השעון, או להפך, בהשפעה מסוימת. עד כאן זה העניין. עכשיו הוא טוען, לכל מערכות יש כמות כזאת מסוימת של אנרגיה, שזה כמה חלקיקים יש שמסתובבים בניגוד למצב של השדה, או בניגוד למה שהיית מצפה שמסתובבים. איבדתי אותך או שעד כאן יש...
בסדר, חושב.
אוקיי. ואז אני אומר, לכל מערכת אני יכול לחשב מצב אנרגיה, שזה סכום כל מצבי האנרגיה של כל החלקיקים באותו זמן. וכל מערכת תשאף למינימום אנרגיה.
מה בדיוק האנרגיה? כלומר, כל הספינים מסתובבים.
אז בוא נחזור שנייה אחת לרשת. מה זה מצב אנרגטי? זה אומר נניח יש לנו כאן שתי נוירונים, ואני אומר שהקשר בין מחויבים, זה אחד, זה מינוס אחד.
לא, אבל אם מדברים על הנוירונים זה לא אנרגיה בכלל, זה פשוט פונקציה מתמטית.
נכון.
אם רוצים לדבר על מה זה האנרגיה, צריכים כאילו לחזור אולי למטאפורה פיזית. כי פה באמת אין משמעות לאנרגיה.
לא, בנוירונים אין משמעות.
אוקיי, שני חלקיקים. נניח נסמן באחד הם מסתובבים כיוון השעון, במינוס אחד הם מסתובבים נגד כיוון השעון, ונניח שהם נותנים להסתובב ביחד, אוקיי? אז מצב שבו הוא באחד או במינוס אחד, זה מצב שבו יש לך עוד אחד.
למה?
צריכה לשאוף למצב שבו הם שניהם יהיו באותו כיוון.
למה אם הם מסתובבים בכיוון מנוגד יש לי אנרגיה, ואם הם לא מסתובבים בכיוון אחיד אין אנרגיה, או יש פחות אנרגיה?
כי הם שניהם שואפים להסתובב באותו מצב. לפחות לכל פעם שיש לך משהו שמנוגד למצב הטבעי, יש לך אנרגיה. זה כמו נניח שאני לוקח אבן, נכון, לוקח את הטוש הזה, אחר הוא נמצא כאן, הוא שואף להיות למטה, יש אנרגיה מסוימת. אני יכול להשתמש באנרגיה הזאת.
אוקיי.
תחשוב שכל פעם שיש לך מצב פיזיקלי שמנוגד למצב
אתה אומר בעצם שפה יש כוח מגנטי, פה יש כוח מגנטי כל הזמן, וכל אחד מנסה לדחוף את השני. הם מגיעים לשיווי משקל כשכוח אחד מתהפך. זה כאילו אנרגיה פוטנציאלית בעצם, כשיש ניקודיות וזה, זה בעצם משהו...
מה למדת?
כלום כנראה.
אוקיי.
קולנוע ופסיכולוגיה, בסדר?
גם קולנוע?
אני למדתי מדעי המחשב, אני לא יותר טוב ממך בתחום הזה.
אוקיי, כן, גם קולנוע.
מה זה קולנוע? לא סיפרת לנו? אתה כאילו עושה לנו את הסרט סוף שנה.
יש סרט סוף שנה? אנחנו רוצים לבחור ז'אנר. אני חושב ז'אנר המערבון, איתמר יהיה שריף, אוקיי? ואנחנו צריכים להגיד מישהי בתפקיד הזונה.
אני חושב שטליה תהיה שריף.
אוקיי. אוקיי, בסדר.
אפשר איתנו אחר כך לפתור את התרגיל?
לא, אני מבין, אנרגיה פוטנציאלית, בסדר, הבנתי.
ואז שוב, יש לך מערכת יותר מורכבת, אתה יכול להניח כמה גורמים שמשפיעים.
וזה האקוויליבריום שכולם רוצים להגיע לכמה שפחות שיהיו אנשים חריגים, כאילו כמה שפחות ספינים חריגים, זה לא נראה לי הגיוני. זה לא האקוויליבריום שמדבר עליו נוירונלי.
אז למה, שוב, יכול להיות לך להניח מצב שבו הקשר ביניהם הוא שלילי, ואז נניח אם זה אחד, זה צריך להיות מינוס אחד. ואז להפך, דווקא אם זה אחד וזה אחד, אז זה המצב בדיוק. ואז יכול להיות לך רשת, מה זה אומר שאנחנו נמצאים במצב של שיווי משקל? זה אומר, אני הכי מנמצא שזה אחד, זה אחד וזה אחד, הקשר ביניהם הוא אחד, אין שום סיבה שהמצב ישתנה. כאילו לעומת זאת זה מינוס אחד וזה אחד, המצב צריך להשתנות בסיבוב הבא.
כן, אוקיי, עכשיו אני מבין.
כל הרעיון של האנרגיה ושל זה להגיד, אני מסתכל על המערכת הגדולה ואני רוצה לך באמצעות מספר אחד להגיד עד כמה היא מועלת להשתנות.
אז זה בעצם אומר לי כמה אני רוצה להשתנות, איכשהו, לא ברור בדיוק למה, אבל איכשהו. זה השינוי, זה המצב ההתחלתי, וכל כך דיברנו לכם שזה לא יהיה אנדרוגני, איך קורא לזה? ארגודי. נכון? אז אם זה, ככל שזה יותר גדול, אז זה יותר בר שינוי. נכון? זה מה שאומר לשנות. ככל שזה יותר גדול או קטן בערך מוחלט או דבר, אז זה אומר שזה יהיה יותר בר שינוי או לא? זה לא דלטה בעצם? זה לא האנרגיה שמתבססת?
אני חושב we have coupled equations, אל תשכח שפה יהיה לך גם עוד משוואות שצריכים להיות אותו דבר מתוך הדבר הזה. זה בסוף כאילו, כן, זה הסופי פה. אז תחשוב על מה שאנחנו עושים בדינמיקה, נגיד שזה ה-X וזה Y, כאילו ב-now you have n dimension. כאילו יש לך I, פה זה תלוי בכל מיני... כן, נכון, אם אתה יכול פשוט להסתכל על זה, אם זה יותר גדול, אז יותר שינוי, אבל זה משפיע על כולם.
וזה הפקטור שבגללו המערכת היא אנרגודית, כי זה כן רגיש למצב התחלתי מאוד, נכון? זה מה שמבטא, או שלא קשור בכלל.
זה אני לא בטוח, זה לא קשור...
אני חושב שזה קשור שיש כמה מצבים של שיווי משקל. אם יש לך מצב אחד של שיווי משקל שאליו יכול להתנקד, אז זה לא תלוי במצב ההתחלתי. תחשוב כמו שיש לך כיור גדול עם חור אחד, ואתה שם בפנים כדור, לא משנה איפה אתה שם, בסוף זה גדול מתוך אותו חור.
כאילו זה יהיה הפקטורים האלה.
זה ברור.
זה יהיה מהפקטורים האלה, זה
הפקטורים האלה?
כן.
רגע, מה זה ג'ק? זה לא קשרים. זה מצב הקשרים.
כן. אז זה הדבר שמשפיע, זה מגדיר בעצם כל הדבר הזה. כאילו זה פשוט, זה המשתנה, זה אותו משתנה, נכון? זה פשוט הנגזרת שלו, זה המשתנה.
השאלה שלי כזאת, אוקיי. זה באחד וזה באלף. ייתן אותו, לא בעצם, לאן זה, לא בזמן אלף. מה קורה? כשהוא אמר שזה צריך להתכנס בסוף, שהוא תהיה את המצב הזה פה, כשהוא אמר שהוא מתאר את זה שהמערכת היא אנרגודית, זה אומר שיש לה הרבה, אפשר לכתוב בעצם קטנים יחסית. לאן הם מתכנסים? הם מתכנסים לאיזשהו מספר כזה? לנגזרת כזאת או ל-MI מסוים?
ל-MI מסוים, וגם, אבל לא רק ל-MI, לכולם, כאילו, לכולם באותו זמן. תחשוב על מה שעשינו בדינמיקה, שהיה לנו את ה-XY.
נכון, בדיוק, נכון.
שם ראינו 3 נקודות פיקס פוינט. זה כאילו סוג של הפיקס פוינט, אם יש פיקס פוינט.
נכון. ומה זה האות הזאתי? א', איך מציירים אותה? ואיך קוראים לה?
זה קסאי.
צ'ופצ'יק לצד אחד, ואז שני צ'ופצ'יקים לצד שני.
כאילו, כמו מה אני מצייר את זה? תעשה קרקטר סיני, אוקיי? בכמה דרכים אפשר לצייר קרקטר סיני? קליגרפיה. מה זה אומר? זה כן מאוד מתחיל לדבר על מצבים פה.
זה מצב, כאילו כל הסט הזה זה מצב מסוים.
של מה? של נוירון בודד? או של כל הנוירון?
כל I נוירון בודד. כשהוא עושה ככה זה מרסק.
זה וקטורים של 100 מיליארד. וקטורים של 100 מיליארד בצורה אחת, וקטורים של 100 מיליארד בצורה אחרת, אוקיי.
זה הנוירון אחד, 2
הנוירונים במצב פי של אחד.
במצב פי. במצב אחד. יש פי מצבים שאנחנו רוצים שהם יהיו... אוקיי.
What we are interested in this program of the asymptotic behavior of the dynamics is in the following. I shall now define the following quantities: m of mu, which is 1 over n psi I mu S I. Now you see, this is the overlap between the actual configuration and one of the selected patterns. And at the beginning, mu.
Over I, right?
Sorry?
That's a sum over I.
Sum over I. This is sum over I for every mu. If Si is exactly the configuration psi mu, then this overlap is 1. Otherwise, it will always be smaller than 1. The initial overlap, such overlap, is 1 over n I psi I mu Si and Si 0, and it is a certain, and certainly what we are interested in is the dynamics of such overlaps. And what we would like to is that the time, I mean, don't take this infinity too seriously, but this is a kind of notation. The infinity here will be 200 milliseconds or something like that. But asymptotically, what we want this to happen, that it will be close to 1, of the order of 1, for one specific mu, say k, and close to 0 for mu different with k. You see, this, I start from an initial condition. This mu here goes from 1 to p. These are the overlaps, the initial overlaps with all the selected patterns. Then the dynamics take all of them. They all these overlaps evolve. And of course, I would like to see
What is K?
two.
K?
K is one selected pattern. Where did I erase it? Yeah, I erased. I had here one selected pattern.
Site. What site?
One of the mu's. Maybe I shouldn't denote it by K, by ni, because these are Greek letters, but never mind. What I mean is that, and of course, it will converge to that particular one, which is maybe the closest to my initial condition. The whole space now, the whole space of configuration is now divided into domains of attraction. And when I start in one domain of attraction, I go to the attractor in that domain. And the attractor in that domain is that configuration. Yes? The question is why it is equal, not exactly to 1, because for two reasons. One is that, as we'll see, maybe, you see, if I can gain large capacity by relaxing the condition that my asymptotic asymptotic state will be exactly this. But if there will be a fixed state, a stable configuration in a close vicinity, namely 1% of errors, then naturally I will still identify it with retrieval. That's one reason. The other reason is that when we are at finite temperature, on the average, it is never one. Because if on finite temperature, a configuration is never stable. We always fluctuate around it. And depending on the temperature, on the noise, we know how strong these fluctuations are. And the stronger the fluctuations on the average, the further away I am from one. And therefore, it's not exactly one. Yes.
אם יהיו שהוא שונה מכ- לאו דווקא אפס, אם יש שני קטעים שהם דומים, קרובים אחד לשני, אז יכול להיות שיש חפיפה מסוימת ביניהם.
Okay, so I did not tell you yet how I choose the examples. I don't want them to be close to each other. Now I tell you, so this is my goal. So let me define these things here. So you see here, oh, I forgot the 1 over n here. You remember, the 1 over n here is from the definition of the JIJs. I forgot that. So you see here, you already have this overlap, because 1 over n, and this is m mu, so what we have here, on the right-hand side, we have the hyperbolic tangent of beta, sum over mu, psi I mu, m mu. See, the sum over j is exactly my definition of these overlaps. Oh, sorry. What? There is one thing that I should. Let's go back to my definition. This would be the definition at 0 temperature, but not at 0 temperature. What we are interested in is this. You see the difference? This is what I am interested in. And therefore, what I have here, namely, this is also 1 over n psi I mu mi, because this is my mi. And therefore, what I have here is what I would like to do now here, in order to have on the left-hand side also such overlap, this is still the average activity at a single site. Let me multiply this equation by psi I mi, and I am not using mu here because I have the index mu over which I sum. Mi is one specific configuration now. Let me sum over I, and let me divide by n. And then I have 1 over, then I will have here m mi is equal to 1 over n psi I me sum over I and this is what, these are the equations that I'm interested in. Now we have P coupled equation for every selected configuration. This ni could be 1, ni could be 2, ni could be 3, and so on until P. And then we have P coupled equations for these overlays. And these are the equations, these are not the dynamic equations, these are the equations at equilibrium. And which, what did I derive?
This is not M?
No, this is the definition. This is my definition.
This is not M. This
It's
is
not
what
an
the
application.
What?
This is a different symbol. It's not M for
I defined M of I with a lower index I as the thermodynamic average of the activity at a single site.
Yes, but on the left.
And on the left here, I have now the overlap. Because this is, at each site, I have a certain average. It's close to 1 or close to -1.
And
These numbers, I mean, it's a number. If it would be 0 temperature, it would be either 1 or -1, depending on the site. If it's not 0 temperature, as we just said, it will be close to 1 or close to -1. These are ones and -1s. And now this tells me how close my configuration is to one of the selected patterns. I specified, you see, whenever there is an S, it is a dynamic variable. Psi is not a dynamic variable. Psi doesn't change. Psi is a selected fixed point.
So
What is, yeah.
okay, when you have 0, the equation afterwards?
When I have 0, when this is 0, I mean, this.
No, well, you said with 0 temperature, you use X, but 0 here, it looks like it's time 0.
I start
Time
at 0 temperature, there is no dynamic average here. At 0 temperature, they're all either +1 or -1. Yeah?
במשנה מככה, אבל זה נראה כאילו הזמן
Yes.
הוא אפס, הזמן אפס.
Look, I start with a fixed configuration. That's my stimulus. Yeah. Then it evolves. As it evolves under the dynamics, and the next step, I will already have a thermodynamic average.
But you don't start with 0 temperature. So why
No, I am not starting with 0 temperature.
So why is time 0?
You asked me why did I not put here?
Yes.
Oh, this is the whole thing. You can put it. No, I didn't. It doesn't matter too much. Suppose, because you see, I can artificially put the system in one specific configuration. But once I let the dynamics operate, then how I go from this configuration to the next configuration is already a probabilistic process. So already in the next step, I need here a thermodynamic average. So if I put it at time number 1 or at time 0, doesn't matter much. You see? I can say that initially I start from a certain probability which assigns this to this a fixed value, but that probability is not an equilibrium probability. That probability will evolve to the Gibbs distribution. So this is a minor point, but okay, this is what I have in mind. So now this is our equation, and this is what we want to explore. And we shall explore this equation, so that our program is to explore this equation in several steps. Greater and greater complexity. And once we finish that and understand everything there is to understand about this, we'll have learned everything we can learn from the Hopfield model. And then we should start worrying about our all the different kinds of restrictions. One is that you see the JIJs that we selected here. They are symmetric. And we mentioned that several times. Now, if everything would depend, everything that we derive, all the phenomenology, would depend on this condition, then it would not be of much help. So we have to talk about that. And then there will be many other such restrictions or such assumptions about connectivity, not everything is connected to everything as we assume here, and so on and so forth. So let's now start with this. So the first thing that we would like to explore is the case, is a very simple case where we have only one such selected pattern. That means P is equal to 1. Just one such selected pattern. But let me just, I'm not going to use it now, but I will use it later, so let me just say a few words about how I select these xi's. So let me assume that I select them, that xi I mu, that the probability of xi I mu being equal to 1 is 1/2, and being equal to minus 1 is also 1. That means that I choose them by random, and I choose each of the bits. What?
Probability is minus, negative?
Sorry, 1/2. Probability also 1/2. Minus 1 is also 1/2. And I choose them independently. I'm choosing here n times p bits, p configurations of n bits. Each of them I choose independently. And if I do that, then the psi I mu, which I define as 1 over n over I psi I mu for every mu, when n goes to infinity, what will it be? 0. It tends to 0. And should warn you. You see, I use here these brackets as average, but this is a different kind of average than the thermodynamic average.
But we don't need the first I in the left
What?
here. We don't need the I here because it's an
No, okay, we don't need that. We don't need the I here because we have a sum, but this is the average of, so that's how we denote, we shall denote that. And that, in that sense, we shall call these unbiased patterns. There is no bias to one of the group. As we shall see, this is also a restriction, which we should give up, and we shall. And we shall. Everything that we do at the beginning is just to make things symmetric, simple, clear. It's not the activity. I mean, at all, if you look at the circle, the activity also, not only the connectivity is sparse, but also the activity is sparse. But we assume that it is the same. And also, if you do that, then psi mu and psi ni, if you define this as sum over I, psi I mu, psi I ni, what is this equal to as n goes to infinity? 0 as long as mu is not equal to ni, so this will be equal to delta mu. Yeah. Familiar with this symbol? 0 and they are different, 1 when they are the same. So what we are saying now, that these patterns which we select at random are not biased and not correlated. This also we shall relax later. Because if we want this to imitate a certain memory or model of memory, then you know that we need a certain similarity concept. There are things which are more similar than others. And here you don't have that. So all these things, I mean, I pile up all kinds of restrictions that we shall relax. And now we go to investigate this, that H, when, I mean, this equation here, when there is only one pattern, and in that case, you see what we do, M1 is equal to. So there is no sum over mu here because there is only one. And then there is psi I of 1, and I can put this bit psi I of 1 into the hyperbolic tangent, because whenever we have, I think we saw that before, whenever you have an antisymmetric function, then you can put the minus f of x is f of minus x, and certainly when there is a plus, it's also the same, so that the sign you can pull inside, and if you put this psi I ni inside, psi I1 inside, there is a psi I1 here, and psi I1 times psi I1 is always 1. Yeah. And then you have sum over I of something which does not depend anymore on I. And therefore, sum of I of something which doesn't depend on I is equal to n divided by n is 1, and therefore what we have here is that this equation, in the case when p equals 1, is the hyperbolic tangent of beta m1, and that's it. And now we want to, and what does it mean now that the configuration psi1 is stable? That means that this equation has solutions what we do. So let's look for the solution. But that's not enough. We shall also have to show you that these solutions are stable solutions under the dynamics. Because we started with a dynamic equation. And then we reduced this equation to an equilibrium equation by just making the derivative zero. But the derivative could be zero in either when the solution is a minimum or when it is a maximum of something. You know. So either when it is a stable fixed point, these solutions, every solution of such an equation for us is a fixed point. And now the question is if it's a stable fixed point or not a stable, right? So now let's start exploring this. So what we have here is let me write here M1, and let me solve this equation graphically, and by solving it graphically, I shall plot now as a function of M1 both sides of the equation and see where they intersect. This side of the equation, the function is equal to M1, and this is a line and this is a line with a slope 45 degrees, with the tangent, the hyperbolic tangent is 1. Now the other one, we already know what it is. The hyperbolic tangent at large variables is 1, at large but negative variables is -1, and the question is what happens here? What happens here? Here we can have two cases. We can have, you know, when beta, you already know, that then when beta is large, going to infinity, then the hyperbolic tangent becomes what? The sine function. And when beta is large, but not infinity, then something like that happens. We could have another case. We could have had another case. And that is, you see, the slope here of this is beta. When beta is larger than 1, this is the case that we have. When beta is smaller than 1, we'll have this case. So you see, when beta, which is the parameter which defines noise in our system, crosses a certain value, the behavior of the solutions changes dramatically. Now let's look first at the case where beta is larger than 1. And so we have here, we have one fixed point at 0. This is always a fixed point because M1 equals to 0 is always a solution. And then we have two fixed points, one solution here and one solution here. Now the question is, what can I say about these solutions? In order to tell you something, to say something about these solutions, There are two ways to do it. One is to look back at the energy and see which has lower energy or higher energy and so on, but I'm not going to do it. There is a simpler way, which is more useful in our case, and that is to look at the dynamics. The dynamics, this, after all, this is the fixed point. If I'm not at the fixed point, or not at equilibrium, then M1 changes under the dynamics, and the change is minus M1 plus the hyperbolic tangent of beta M1. Yeah? This is the dynamic equation. So if I am, suppose I am now here. Suppose M1 is equal to this value. If M1 is equal to this value, this is not a stable value of M1. So what happens here? You see, here, this curve is higher than this curve. Therefore, the right-hand side is negative. Therefore, when I am here, the dynamics will take me in this direction. If I am here, here you see the hyperbolic tangent is higher than m, therefore the right-hand side is positive, and therefore the change will be positive, and the dynamics will take me in this direction. And the same thing will happen here. If you analyze it the same way, you will find this thing here. So you see, this is a stable fixed point, because when I am around it, not there, I converge to that fixed point. This is a fixed point, but it is unstable. This again is a stable fixed point. So you see, here when beta is larger than 1, then I have two stable fixed points, M1 and minus M1. Minus M1, you see this symmetry between plus and minus is another artifact. It's an artifact of our choice of this variables plus minus 1. This is not natural. This should not be there. We should find a way to interpret it, to get away from it. But what we show here again is that this psi1 is depending on the noise. If the noise is too large, then it is not a fixed point. If the noise is not too large, then it is then we have what we call this is a fixed point, but the thermodynamic average of the value is smaller than 1, because the fluctuations around that fixed point are quite large. If beta is larger than what I do, for example, if beta is here, this is 1. If beta is here, then you see M1 is closer to 1. Because the larger beta, the smaller the fluctuations. You want to לשאול?
כן. שמה שלנו, התשובה נראה לי שקיבלנו, היא הייתה עבור MI, לא עבור MU.
Okay, you are right. So do a small exercise and convince yourself that it is the same dynamic equation. Okay. So this is our. So this is what we have. One other plot that it is worth mentioning here is this one. Let me write here T equals 1 over beta. T is 1 over beta, T the temperature, and here M1. Now, when T is 0, then we have a fixed point M1, which is equal to 1. And also another fixed point, 1 and minus 1. When T is equal to 1, namely T larger than 1, beta smaller than 1, then our fixed point is 0. Our stable fixed point is 0. The noise completely destroys those fixed points. Here we have something where the noise is not too large, we are very close to 1, and then it goes to 0, and we have something like that. We have another fixed point here, which is not stable. So you see, when you look at this, as a function of this parameter beta, or T, which is our noise, the dynamic behavior changes dramatically. We have one fixed point, 0. Then, at this particular point, we suddenly generate 3 fixed points. The one that was previously stable is now unstable, and 2 other stable fixed points take over the dynamic behavior of the system. And this something like that we refer to as, this kind of behavior, and we should encounter that as we explore other dynamical systems or complicated dynamical systems. This phenomenon is referred to as a bifurcation.
When m is not equal to 1, there are a lot of stable states, right? Because the overlap can be very strong.
No, in this case, when there is only one.
When m is not 0, but when the stable state is between 1 and 0, so there will be a lot of stable states.
Depending on the temperature. Each temperature there is one stable state.
But it's not one state, because the overlap can be created.
No. What we call a stable state thermodynamically is not a configuration. What I am saying is, if you want to look at configurations, if you can, then you have this psi, and around this psi, your system all the time, fluctuates, but it remains in a certain neighborhood here. It fluctuates all the time. By then, what we mean by stable state is that a certain parameter which we define is this average overlap. That is stable. That does not change. This is the parameter of our state. So we did this, and now the next thing that we would like to do is to explore the following. Now we assume that there is no thermodynamic noise. So T equals 0. No thermodynamic noise, but we want P to be larger than 1, and the question is, how many p's can we embed in our system, choosing them as I specified, so that all of them will still be fixed points. And we'll see that there is a limit. You can imagine, if you put too many of them, they start to interfere with each other. So that's what we want to explore. What is that limit? This is what we refer to in our jargon as the memory capacity. And when there is no noise, then we have a very simple criterion for stability. We do not have to look at that equation for the time being. The criterion of the stability, a bit, the value Si will remain Si in the course of dynamics if Si times Hi is positive, where Hi is what we know. So the question, if a certain configuration Xi1, say, if that configuration is stable, reduces to the question if Xi I1 Hi is larger than 0 for all I. If that holds, then this configuration is stable. And then I will want to see what is the condition that such a configuration is stable, and later what is the condition that all the configurations. And so this is the thing. So what is this explicitly? Xi I1, and then we have 1 over n, sum over mu, and sum over j, Xi I mu, Xi j mu, Xi j 1. Because you see, this is Jij, this sum over mu, 1 over n, Xi I mu, Xi j mu is Jij. Now the Si, the Hi is Jij times Sj. But my Sj, that's what I'm investigating, I'm investigating if this configuration is stable. So I have to put here the Xi j of 1. And the question is if this is bigger than 0. Yeah? So now the analysis of this question, we refer to this as signal to noise analysis, a common useful concept method tool in the study of such systems, and we shall encounter that also on several occasions. So what we have here, let me first split this sum into mu equals to 1 and mu different than 1. When mu equals to 1, I get here mu 1, then everything here is 1, right? Everything here is 1. I have still a sum over j. Sum over j of 1s is n, divided by n is 1. Actually, we have to be a little careful because J is, in our assumption, J is never equal to I, so the sum over J is n minus 1, but that I ignore. Yeah? And so what we have here is 1 plus psi I 1 sum over n, sum over mu larger than 1, because 1 I already used, psi I mu, psi j mu, psi j 1. And so this is psi I h I, and now my question is the following. You see what I have here? I have divided this into a signal. This is a signal. It's clear, standing out, and into something which is a random variable, fluctuates. And the question is, of course, what kind of random variable it is. And random variable, this is the signal, and this is the signal, and this is the noise. So we have the signal to noise analysis here. And we want the signal to be larger than the noise, significantly. That's what I mean by noise. Here I have an n here, so yes, you're right.
And a sum over J.
Sum over J. Also. So now I want to look at this noise term, and the noise term is the noise term here is define it as gamma 1, or gamma 1 is still an index I, which I should ignore now. This will hold for every bit, of course. So now, so what kind of random variable it is? What is the average of gamma? What's the average of that?
What's gamma?
These are bits. I mean, they are all bits. They are all uncorrelated. So it's 0. They're all uncorrelated, and therefore each of one, the average is 0, and therefore it is 0. So we have this. Now, again, this is a random variable, which is a sum of many random variables. And you have anybody, I don't know, if you took your course in probability theory, any random variable, which is a sum of many random variables, is a normal, is a Gaussian random variable. Here we have many random variables, the Gaussian distribution, with a binary. We have many binary random variables. The sum of many is always a Gaussian.
How many?
How many?
0. What's the minimum
How many? What's the minimum? Look, a finite will always become close to that. We're talking about an infinite limit. How close asymptotically you get to the Gaussian, I don't know. But this, I assure you, is a Gaussian distribution. So what we have here, So if it's a Gaussian distribution, so we know that this is 0, and then the question is what is sigma? What is sigma squared? And sigma squared is, of course, the average of gamma 1 squared. This is what we are interested in, and to do that, let me here define, say, gamma, just to make some short, is defined as sum over mu, sum over j of let me write eta I mu, eta j mu, whereby eta I defined psi 1 psi mu. This is my definition, just to make it the notation shorter, and then gamma 1 squared will be 1 over n. This is what's written there. This will be 1 over n squared mu prime j prime eta I mu eta I mu prime eta j mu eta j prime mu prime. Is this clear? That is, when I take the square of that sum, this is what I get. Look at it for a while, and then we continue. Now, yes?
אם תיקח את ה-J ותחום על כל ה-J, תקבל דלטה 1 מיו, לפי הגדרות שלי קודם.
בסדר.
אז למה לא עשית את זה?
Look, what I am saying is this the mu here are, the mu are now, every mu here is different from 1. Every mu and mu prime is different from 1. Every j prime is different from I don't know. So this is the expression. Now we have to take the average of this. What's the average of this? You see, whenever j is different from j prime, and mu is different from mu prime, again, we have these products, sum of products of random bits that are uncorrelated. So the average of such a product is the product of the averages, and each such average is 0. Unless mu is equal to mu prime, and j is equal to j prime. Yeah. And when that happens, everything here is 1. And we have sum over 1s. How many 1s do we have? Combine the two answers and you are right. P times n. Because you have the sum over mu, you sum over j, p times n divided by n squared. So this is equal to p over n, and we define this as alpha, and this parameter alpha will play the central role in our discussions of the Hopfield model. But right now we can proceed. So now we have sigma squared. Now we have a random variable, and this random variable, the probability of gamma is 1 over 2 pi alpha e to the minus gamma squared over 2 sigma. I think it should be 2 2 alpha. No, it's 2 sigma squared here. This will come in later. Is 2 alpha. And this is, I think, this is yeah, this is it. This is it. So now, what is? Now our question is, we still come back to this question, what is the probability that this will be larger than 1? This is exactly the probability that this will be larger than minus 1. If this is more negative than minus 1, then this configuration is not stable, or at least that bit of that configuration is not stable. So this is what we are asking now. The probability of that is the probability that a psi 1 psi I hi is larger than 0 is equal to minus 1 to infinity 1 over 2 pi alpha square root e to the minus gamma squared 2 alpha. This is gamma 1 or what?
No, but just
the gamma. Yeah. So this is it. So you see what you have here is the following. This is the normal distribution. This is minus 1. This, I mean, the width here is somehow determined by alpha. You see, the larger alpha, the broader this distribution is, and the more area there is on the left side of minus 1. The left side of minus 1 is the probability of an error at site I. Is the probability that this site is not stable, namely the other one is stable.
If we always be smaller than the probability that we not get error, even when p is infinity. Even when p
Yes.
is like infinity, the probability of error will still be smaller than the probability
How do you know?
not get error. כאילו תמיד השטח מצד שמאל יהיה יותר קטן.
we have to know to say the following. Of course, if P is finite, or if P over n goes to 0 when n goes to infinity, then every one is stable. Because then alpha shrinks to this, and then you've already shown that every configuration chosen as we did, if we choose them differently, then it's a different story. And I show you what is the role of the statistical properties of these size. But once we've chosen them this way, when alpha goes to 0 as n goes to infinity, certainly when p is finite, certainly no matter how big p is when it is finite, but smaller than every configuration is stable. That's one. Now I want to do a little more. I want to ask, what is the limit? Suppose p is larger than n. Suppose p is of older n, or something of that kind. What is the maximum p which will still guarantee that everything is stable? And so now let me do that, and let me define gamma squared divided by 2 alpha. Let's say, define that as x squared, and then you will have, once you do that, you will once we do that, we'll have 1 over pi minus alpha to infinity e to the minus x squared. This is our probability now. If I'm not, I believe this is correct. Now what does this remind you of? This function here. You see, if I take, I can divide this into 2 parts. From 0 to infinity, this will be what? 1/2. And then from 0 to square root of 2 alpha, or to 1 over the square root of 2 alpha, this is what?
Something smaller than half.
That's true, but this is a function which we already were already familiar with. We met it once. This will be 1 over, remember the error function? So this is it. And now we want to do the following. We want to see, when alpha is p over n, when alpha goes to 0, the argument here goes to infinity, error function of infinity is 1, and everything is stable. But now we want to do this fine, the fine details. And for that, we would like to use the following property of the error function, namely its asymptotic behavior. When x goes to infinity, the error function goes to 1 minus 1 over pi x. You can look it up in, I don't know if it still exists now that you have with the computers, but once we had these tables of functions with all kinds of properties and logarithms. There are whole books that we had on our desks always, and there we could look up all kinds of representations, asymptotic behavior, integrals, definite, indefinite, of every function you can imagine or not imagine. But then you will find that this is e to the minus x squared. And therefore, if you apply this here, then you have the probability, and I'll write it again, psi I1 hi bigger than 0 is equal to, I plug this in here and I have 1 because this will be another 1.5 plus, and then I have to use this, and x is to alpha. I think that what I will have here now, first of all, it will be e to the minus x squared minus 2 alpha, and here I will have something which is alpha over 2 pi, and this is my result, minus, sorry. So this, the right-hand expression, is the probability for site I to be stable. What is the probability of site I to be unstable? This is the probability, because the two of them have to sum up to 1.
Should there be a 1 half?
What?
Should there be a
What? So if this is the probability, if this is the probability of an error at site I, then the number of errors in configuration 1, that's what I'm looking at, one specific configuration, is n times this. Is n times this. And I would like, in order to assure the stability of one configuration, I would like the number of errors to be less than 1. The number of, I mean, this will be my limit. When the number of errors is 1, then the configuration, the whole configuration is not stable. There will be at least 1 error. Yeah? So this is what I want to do, and this is now easy. This is the last step, and we are almost done. And we are almost done here. And I take the logarithm of both sides of the equation. So the logarithm of this is 0, and then I have ln of n, and then I have minus 2 alpha and then I have ln of this, and this with ln is negligible compared with the other two terms, and what I have here is, you see, there is here a p over n, and the larger p, the more negative this is, and therefore there is a p max. The p max is when this is equal to 0, and p max will be equal to n over 2 ln n. And this is my final result. And you see this, the p now if I want just one small addition to that, here I required that one configuration is completely stable. If I want all configurations to be completely stable, then the number of errors will be p times n, because we have p times n bits. And if this p, I replace by n times alpha, then I'll have, in this case, I'll have n squared, and then there will be an alpha times alpha to pi e to the minus 2 alpha, e to the minus 1 over 2 alpha, and I shall have the same argument for this one difference. I'll have here ln of n squared, which is 2 ln, and therefore here I'll have the result 4 ln n. This is a small, fine mathematical point, not really of great importance. What is important is that we have shown that in our system, this is the capacity if I require that all bits are stable. I already told before that even at zero noise, it is not an essential requirement, because even if there is a fixed point in a close neighborhood of the one I selected, I will still be happy. And we shall later, next time we meet, we shall relax even that condition, the requirement that every single bit has to be stable. We shall put a more relaxed condition, and we'll see that we shall be able to increase this capacity dramatically. Yeah.
Can you explain why the right term is neglectable?
Okay, look at it, because it's the square root of n over p. You know that it's, look, it's of order ln. If you put your result inside.
N is larger than 6.
Yeah. Okay. So this is the one thing I am now. We had. I think I should not start a new. I don't want to start a new topic now. So I'll bid you farewell. We do not have a lecture next week. Yom Ha'atzmaut. So we shall meet again in 2 weeks. But between now and then, you will have two exercise classes. And therefore, there are two things which I wanted to show you now. They are very simple. I'll ask Tal to do it next time. And the one thing is to show you how important this statistical requirement is, that the patterns that we select are unbiased. Once they are biased, we apply the same signal-to-noise analysis. With this selection of